This is video A of the binomial theorem. The binomial theorem describes the algebraic expansion of powers of a binomial. If I were to ask you to expand the expression 3x minus 2 to the 10th power, you would most likely give up after about the third exponent or so. The binomial theorem is a shortcut, and the first few coefficients can be represented by the triangular array of Pascal's triangle. Notice how each row begins and ends with the number 1. Each of the other numbers, if expanded to a plus b to the n, would be found by adding the two closest numbers above itself. So, when finding the other values of Pascal triangle and how the system works is that 2 is found by adding 1 and 1 right above it. 3 is found by adding 2 and 1 above it. Similarly, 6 is added by adding 3 and 3 above it. Pascal's triangle helps us when we expand the binomial expressions. In order to find the coefficients, we need to describe Pascal's triangle a little more in detail. The first row is officially called row 0, where a plus b to the 0 is represented, since anything to the 0 power is 1. This is officially row 1, where a plus b to the first power is represented by the coefficients listed here for 1 and 1. We will get more practice as we expand these expressions so you can see how Pascal's triangle is related to the following binomials. So we'll go ahead and complete these expressions as we go down. We have row 4, which looks like it's at row 5, but officially it's row 4. And we can now see how we could possibly be using these coefficients. Okay, scrolling down to the second section, let's go ahead and expand these binomials. Well, anything to the 0 power is 1. And if we take a look at Pascal's triangle, yes, we see that the row 0 is 1. Expanding a plus b to the 1, we just end up with a plus b. And the coefficients happen to be 1 and 1, which is the first row of the Pascal's triangle. As we expand a plus b to the second, we end up with a squared plus 2ab plus b squared. And those coefficients also match Pascal's triangle with 1, 2, and 1. In row 3, okay, let's go ahead and expand a plus b to the third, and it does indeed match Pascal's. B to the third is a cubed plus 3 times a squared times b plus 3 times a times b squared plus b cubed. And those coefficients, 1, 3, 3, and 1, match the third row. Expanding a plus b to the fourth, we end up with a to the fourth plus 4 times a cubed times b plus 6 times a squared times b squared plus 4 times a times b cubed plus b to the fourth power. A plus b to the fifth power, we can go ahead and expand that. A to the fifth plus 5a to the fourth times b plus 10 times a cubed b squared plus 10 times a squared times b cubed plus 5 times a times b to the fourth plus b to the fifth. So some thoughts to ponder. In each term, what is the sum of the exponents? So if I went ahead and let's take a look at a plus b to the fourth power. As we go down each of the terms, I can see I have 4 powers here in a to the fourth. A to the third plus b to the 1. I know we don't usually add bases, but we're just looking at the pattern. The sum of 3 and 1 is 4. Going down to the third term, a squared plus b squared. The sum of these two exponents is 4, and a to the 1 plus b to the 1, the sum of those exponents is 4. So we're seeing this pattern that the sum of the exponents add to the exponent n, the power of the binomial. Now, how can we find the coefficients of these terms? Well, we can look at the numbers in each row of Pascal's triangle. Now we can describe the pattern of the exponents of a in each term and the exponents of b in each term. The first term is a to the n, and the exponent on a decreases by 1 in each successive term. So in our example of the fourth expansion here, I have a to the fourth, a to the third, a to the second, a to the first, and then there is no a, or it's a to the 0 with b to the fourth. The exponents of b increase by 1 in each successive term, and the first term of the exponent of b on the first term is 0. It's b to the 0, so it equals 1, and that's why it doesn't show up. And the last term is b to the n. So we have b to the 0, we have b to the 1, b squared, b cubed, and b to the fourth. So how many terms do we have in each of our expansions? So taking a look at our example again here, with our fourth power, we have 1, 2, 3, 4, 5 terms when we expand it to the fourth power. If we were to count the number of terms in the fifth power expansion, we have 1, 2, 3, 4, 5, 6. So indeed, there is one more term in the polynomial expansion than there is in the power of the binomial n. There are n plus 1 terms in the expanded form of a plus b to the n power. As your got it question, I would like for you to expand Pascal's triangle one more row below and find the coefficients that should match in this pattern, and expand a plus b to the 6th power. And we'll move on to number 2 and expand 2x minus 3 to the 4th. So this is where the binomial theorem comes in handy. If we were to expand 2x minus 3 to the 4th, I would go ahead and actually rewrite this as 2x plus a negative 3 to the 4th power, and that will help us out when we identify our a's and our b's to find the pattern. So let's go ahead and start. Following the binomial theorem expansion, we have our first a to the 4th, which is 2x to the 4th power. Then we have our first coefficient, which is going to be 4 times 2x to the 3rd times our b, which is negative 3. Let's continue on expanding. Our next coefficient in Pascal's triangle is 6, and we have that multiplied by our a, which is 2x, and square that times a negative 3 to the 2nd power. Now you can see how the 2x power is descending as we are increasing our and going along with our expansion here. And my 2x power is decreasing and negative 3 is increasing. And a good way to not get lost with the terms is we can go back through and double check to make sure that our powers are indeed ascending and descending. But first of all, I'm going to go ahead and verify that I have my coefficients correct in my Pascal's triangle. So I have 1, 4, 6, 4, and 1 represented. For my a's, I can see that I have my exponents belonging to 2x is 4, 3, 2, 1, and we have a 0 in this last term. So looking at our b, which is negative 3, that's 1, so it's represented there. I have 1 power there, 2, 3, and 4, and I do have everything that I need to go ahead and solve the remaining part of this expression. So going through and remembering as you go ahead and solve that 4, the 2x to the 4th power, you must square or raise the 2 to the 4th power as you're remembering and recalling your properties of exponents. And I can go ahead and rewrite everything as I'm expanding and calculating things out. So I have 6 times 4 times x squared times 9 plus 4 times 2x times a negative 27 plus negative 3 to the 4th power. Okay, taking a look at that and calculating things out, I have 16x to the 4th minus 96x cubed plus 216x squared minus 216x plus 81. And that is the solution for our binomial expansion of our expression, 2x plus negative 3 to the 4th power, and everything checks out. Okay, wrapping up video A, let's go ahead and talk about the binomial coefficient. For non-negative integers n and r with n greater than or equal to r, the expression n over r is called the binomial coefficient and is defined by, let's go ahead and write this definition, n factorial over r factorial times n minus r factorial. And now in your calculator you can go ahead and find the factorial button. You could also probably find this key and choose r somewhere in your probability link. But we will go ahead and evaluate some small expressions that we can do by hand. So using our definition, 6 over 2, we are going to say 6 factorial over 2 factorial times 6 minus 2 factorial, which is equal to 6 factorial over 2 factorial times 4 factorial. And pulling out the 6 and the 5, go ahead and see if my pen is working, which is 6 times 5 times 4 factorial, all over 2 times 4 factorial. And so that ends up, the 4 factorials end up canceling out, so we just end up with 6 times 5 over 2 factorial. So we have 30 over 2, and this whole expression is equal to 15. Really simple mathematics. If you can go ahead and answer the got it question to evaluate 8 over 2. That will conclude video A, and we'll move on to video B, which is the formula for expanding binomials.